Hello. In this video, I perform a quick thermomechanical analysis of a motorcycle brake disc. This technique is useful when comparing the performance of different disc designs to determine the optimal geometry. First step. Create new document and set the unit system before doing anything else. Next, import or create the geometry. In my case, I'm importing a brake disc geometry that I reverse engineered from a picture. I had to take this approach because I couldn't change the unit system after the geometry was created. Once the geometry is ready, we need to partition the side surfaces to apply the analysis boundary conditions. These partitions can be created using the Part Workbench. Create a FERS partition sketch to the disc side surface. Then create corresponding sketch to another side, and you can copy the partition lines from FERS sketch. Then repeat for brake pad area. Now, first click the partition sketch and then click the Geometry Feature Control button pressed. Click the Boolean fragments. Repeat for all the partition sketches. Partitions are ready. Next step is to create the FE model. Open FEM Workbench and create the analysis container. Apply the material parameters to the model. I tick the Use this task panel option and input the parameters without creating a new material in the library. Apply the fixed boundary condition to the bolt holes. Apply the brake pad force to the surface. We have to make one more sketch for the force direction. I apply a 10 kN force, which roughly corresponds to 1.2 G braking on my bike. Apply the initial temperature. Apply the hot surface temperature. Apply the heat flux boundary condition to the cooling surfaces. We'll use a steady-state solver, so let's set a relatively high value for the film coefficient. This approach ensures conservative stress results for the spokes due to the high temperature gradient. All boundary conditions are set. Let's mesh the model. I set the element size to 5 mm and the element type to first order for initial testing of the model. Later, the element type can be switched to second order, and the element size can be refined until the results stabilize and become consistent. Click Solver Calculix Standard button. Double-click Solver CX Tools to open. Set Analysis Type to Thermomechanical, set the solver working directory, and hit Write IMP File button. Four minutes later, the IMP file is ready. Now hit the Run Calculix button. Solver is ready in 2 minutes. Here is the results of solver iterations. We are interested in the last one. Here is the temperature field. From the stress results, we can see that the maximum stress is near the yield stress of tempered 420 stainless steel. If we run the analysis for brake pad force separately, we can see that it has a relatively low effect on stress compared to the thermomechanical stress. This thermomechanical stress is what causes the disc to warp when the yield stress is cyclically exceeded. With the pipeline result, we can have the color bar for the field value. Displacement can be scaled to see how the geometry behaves. I ran the simulation with second-order elements and obtained a maximum stress result that was over 30% higher. Writing the input file took 27 minutes, while solving the model took 2.2 minutes. That's it for now. Thanks for watching, and please hit the like and subscribe buttons and leave a comment. Bye-bye.